Hi, so this is a lecture that continues from the last one on dipoles and quadrupoles and forces on dipoles and so on. So in the previous lecture, we talked about the force acting on a dipole, and it turned out that if you have an inhomogeneous electric field, then it's like the sort of the gradient of the electric field is what couples to the dipole moment and creates a force on the dipole. So the other quantity of interest that we can consider is the torque generated by the external electric field acting on the dipole. And so here I draw the same diagram as before. Pretty general charge distribution function and a pretty general electric field profile. And given those, we can ask if there's any torque acting on this charged matter. And the question boils down to mathematically computing this integral of r cross f, where r prime here is some location inside this matter, and force is, of course, given by the local charge density multiplied by the local electric field. And given this general expression, we can expand the electric field just as before. So we start off with some leading term of the electric field taken at some arbitrary position inside the charged matter, and keeping presumably up to first order terms to see what happens. And but luckily, it turns out that even this leading order term has a non trivial effect, because if you just insert this leading order term into the torque formula, then it turns out that you obtain a very simple form, which is this integral, which is nothing but the definition of the dipole moment for that charged matter. And this is the final form. So P cross E, the cross product of these two vectors, is equal to the torque acting on this dipolar system. So to create a torque on something, you don't even have to have a non-uniformity in the electric field. As long as the material at hand has a finite dipole moment, and then you just apply some electric field, even a uniform one, then there is a torque acting on this matter, and this thing will rotate under the influence of a non-zero torque. And the torque only vanishes if the dipole moment aligns itself parallel to the electric field. And unless there is such an alignment, the dipole moment will continue to rotate in an effort to align itself with the electric field. And this is something actually we know pretty well from freshman physics. But I thought here I would give a sort of a more sophisticated derivation of something that we're already quite familiar with. And so you can ask, of course, what happens if you insert this next order term into the torque. And you can sort of expect that the integral will pick up some effect from the quadrupole moment, Qij, but you can also expect that the final expression will be exceedingly complicated, and then you have to start wondering whether this is really necessary to go through all that computation stuff. And I personally don't really see much point in doing that, so I will just skip that nasty piece of calculation and just remind you that in many in pretty much all aspects of physics that I am aware of, this formula is already good enough for doing things. At least that's what I can tell you from my own experience of doing physics for the past couple of decades. Okay, so now the next question that I want to ask is the question of dipole potential energy. Previously, we talked about the potential generated by the dipole, but here what I want to talk about is not that. Is actually the potential energy felt by a dipole in the presence of some external electric field. Okay, so I hope you are keeping track of these differences. Okay, so to derive the potential energy formula, we have to go back to this force result we got from the previous lecture, which said that the force acting on a dipole due to an inhomogeneous electric field is given by this form. Okay. Okay, so now we're going to play a little bit of a trick. And the trick is the following. We're going to just write down a component of the force, component J, which will be like this form. However, you can subtract and add back this term. Okay, and you're not changing anything. So you subtract this form here and then put it back here. Okay, so this is the same as this form that we got previously. However, something nice happens now because this is actually nothing but the curl of the electric field. Okay, and we know from earlier discussion that the curl of the electric field is 0 as long as there's no time dependence in the field distribution. So that's very nice. Then we can, because we can just remove this term from consideration and just work with this thing instead. And the reason why this thing is nice is because now the indices have changed. And the indices have changed in a way that makes it possible to express the force as the gradient of some scalar object, which is P dot E. Okay, so if we define this thing as the potential energy of a dipole in the presence of an external electric field vector E, then we can deduce the force acting on that dipole through the usual rule of taking the gradient of that potential energy and putting a minus sign in front. Okay, so we can just as well regard this thing as the potential energy of the dipole object in the presence of an electric field. And the potential energy definition itself does not require that the electric field be non-uniform, right? Even for uniform electric field, you can still define the potential energy in this way. However, if you want to see the situation where there's a force acting on the dipole, then you would have to consider the inhomogeneous situation where the electric field varies from space to from position to position. Okay, so the next in line is the discussion of dipole-dipole interaction. So here the situation we are considering is when you have a pair of dipoles at a substantial separation. So the two dipoles basically see each other as point-like objects but with still this information about the dipolar structure intact. And just recall what we have learned so far. We have learned what is the electric field created by this dipole, for example. That's the first thing we learned in the previous lecture. And now what we learned just now is the potential energy felt by this second dipole due to an electric field acting at the location of this second dipole. Okay, so that means we can combine those two pieces of knowledge to write down what amounts to the interaction energy between a pair of dipoles. And the procedure is not hard. It's just a matter of bringing back the things we already know. And first of all, we know that the field generated by the first dipole here at the location of the second dipole will be given by this form. Okay, so here we have the dipole moment of the first dipole P1 showing up, and R21 is just the separation between the two locations given in this way divided by its length. Okay, and secondly, the potential energy felt by the second dipole is given by this formula that we just derived. So all we have to do is to take an inner product of this thing with the P2 and put a minus sign in front. And that will give us this form as a final result for the interaction energy between a pair of dipoles. And you can see that this is symmetric under the interchange of the two labels. If you switch 1 and 2, you still get the same expression. And what that means is that if you were to start off with the opposite, in the opposite manner, first consider the electric field generated by this second dipole at the location of the first dipole, and then proceed to consider the potential energy due to the electric field on the first dipole, you would still get exactly the same expression that we got through the opposite way of deduction. That explains the symmetry of this expression under the interchange of P1 and P2. And I'd like to emphasize that although this expression is derived for a pair of electric dipoles, surprisingly, exactly the same expression applies for the interaction energy between a pair of magnetic dipoles. Why the magnetic dipolar energy has to be exactly the same as the interaction energy between electric dipoles? To me, that's not entirely obvious why there should be this perfect equality. Maybe has to do with some symmetry consideration, which I haven't really gotten around to yet. But anyway, that's a fact. And this dipolar energy being pretty long-ranged. By long-ranged, I mean that even if two dipoles are far apart, there is a non-zero effect, weak but non-zero interaction effect between those two dipoles, right? Because although the dipolar interaction energy falls off, probably this is a typo. I should say r cubed, not r squared. So sorry about that. So although the energy decays as cube of the distance, and this is of course much weaker interaction than the Coulomb interaction, which falls off only as the first power of the distance. However, still, cube is not nothing. So for a pair of dipoles that are a substantial distance apart, you still have some non-zero interaction effect. And that tends to have a global effect on the arrangement of magnetic dipoles in ferromagnets, for example, and create all sorts of exotic domain structures that one can image through various imaging techniques like magnetic force microscopy and so on. Okay, so next on is the quadrupole moment. An intuitive way to think about the quadrupole moment is to view it as a pair of dipoles with opposite orientations of the dipole vector. Okay, so if you have a one dipole with P oriented this way, and a second dipole with a dipole moment exactly oriented in the opposite way, then the net dipole moment is zero. However, the quadrupole moment of this combined system is not necessarily zero, and that's where the concept of a quadrupole moment can play a role. Okay, so I'd like to remind you that the potential, electrostatic potential due to a quadrupole was given by this pretty exotic and complicated looking formula. So this is a product of two tensors basically. You have this tensor Qij, and you have this second tensor, and the potential is obtained as a contraction between two tensors. And the definition of the Qij tensor was the following. Okay, so this is an integral of the charge density weighted with some components of the coordinates, either x or y or z. And I mentioned that altogether there are 9 different components to the Qij. But actually, that was a slightly misguiding piece of information because Qij has certain symmetry built in. For example, Qji is the same as Qij because if you interchange these two indices or two coordinates, it's still exactly the same integral as before. So, there's this symmetric condition which is always true. So that means if you can compute the Qij, Qxy, for example, there's no need to further compute the Qyx because that will be exactly equal to Qxy anyhow. And that means altogether there are 6 independent components and not 9 independent components. However, it turns out that there is even a way to reduce the number of independent components further down to 5 rather than 6. And the trick is to make this, the trick is to come up with a new definition of the quadrupole tensor, which is traceless. Now, to come up with the traceless tensor, just note that this thing we have here, okay, so what we have here is Qij multiplied by this canonical delta portion of the of this definition, and you just write out this thing, and then you realize that it's entirely okay to write this thing in this fashion. So you're basically transferring the canonical delta function to the RIRJ part. And once you do that, it will become obvious that this definition that we had earlier becomes equal to this modified definition, okay, where the new tensor Q prime has this sort of component. So in comparison to the previous one, the previous definition only had r prime I, r prime j, but the new one had this have this extra tail, sort of a subtraction by this thing with a canonical delta, and then this canonical delta thing that appeared on this side now got absorbed into the definition of the quadrupole tensor itself. And that's why this part now looks to be simpler. Okay, so since these two expressions are identical anyhow, it doesn't matter which one you use, but people typically prefer this expression over the first one. For some reason, I guess the main reason to prefer this definition over the other one is that not only is this new tensor symmetric as before, but it is also traceless. The traceless condition can be proven in a simple way by just equating the two indices. So if you have a q prime I, just write out the expressions for q prime I, and you'll discover that this is basically zero. Okay, since you're integrating zero over something, then the result is, of course, a zero. Okay, so under this traceless condition, then you have not 6, but only 5 independent components. And the independent components are qxy, qyz, and qzx. And only 2 out of these diagonal components are necessary because the sum of these 3 things will be 0. So as long as you know what these 2 values are, the third value is automatically determined. And perhaps for that reason, it's common to define this quantity as the quadrupole moment of an object rather than the previous definition that we had earlier. Okay, thank you.